Hello, bachcho. Welcome. Today, we are going to tackle a very important topic from our Unit 4, Moving Charges and Magnetism, and that is the Biot-Savart Law. Now, I know the name sounds a bit scary, but don't you worry. I promise you, by the end of this session, you'll understand it so clearly, you'll be completely confident for your exams. No more fear, okay? Chalo, let's begin.
So let me start by asking you a simple question. Have you ever wondered why, if you bring a compass near a wire that's carrying current, the little needle suddenly comes to life and starts to dance around? Well, this is exactly what a scientist named Ørsted noticed almost 200 years ago. He was the first person to realize that an electric current actually creates its own magnetic field around it.
So this is basically what Ørsted was seeing. The current flowing through the wire creates these invisible circles of magnetic force. And the compass needles, they just obediently line up along these circles. This very simple observation, it pointed to a really deep connection between electricity and magnetism. And that's exactly what we're going to explore now with a very powerful law. Okay, so here's our game plan for today. We'll start with the mystery of the force itself, then we'll build a nice mental picture of the field. After that, we'll get into the official law, the one you need for your exams. We'll use it to solve a problem, and then, very importantly, we'll look at the common traps to avoid. And finally, we'll wrap it all up with a summary. It's a clear roadmap, so let's get going.
Right, so our first stop, understanding this mysterious force. And everything starts with one simple but really profound observation.
This line, it's straight from your NCERT textbook, and it's the absolute key. Ørsted told us that a field is produced. But as good physics students, we need to know more, don't we? We have to ask, how much field? What is its strength? And which direction does it point in? For all of that, we need a formula.
But before we jump into any scary-looking formulas, let's just relax a bit. Let's build a simple picture in our minds first. I'm going to give you an analogy that will help you imagine exactly what's happening here.
So I want you to imagine a long wire is like a garden hose, a water pipe. Now focus on one very tiny section of that wire, which has current flowing through it. We call this tiny piece a current element. I want you to think of this element as a tiny little water sprinkler. But instead of spraying water, it's spraying a magnetic field all around itself. And this picture here, it shows you exactly what I mean. See that small piece of the wire, the one we call IDL? That's our little sprinkler. And it's creating a tiny magnetic field, which we call dB, that goes in circles around it. Our entire job with the Biot-Savart Law is to figure out a way to calculate the strength of this dB at any random point in space, like, say, this point P. All right, now that we have that mental picture of the sprinkler, we are ready for the main event. Let's look at the official law. This is the one you must write in your exams if you want to get full marks. And here it is. The magnetic field dB is equal to a constant, mu naught by 4 pi, times the cross product of the current element IDL and the position vector r, all of it divided by r cubed. Now I know, when you see a cross product, it can look a bit intimidating, but please don't be. Just think of it as a special machine. You put in two vectors, dl and r, and it gives you a third vector, dB, that's perfectly perpendicular to both of them. It's a fantastic tool because it gives us not just the strength of the field, but also its direction, all in one go. Let's break this down using the diagram. It'll make it much clearer. See IDL? That's our tiny current element on the wire. P is the point in space where we want to find the field. R is the vector that goes from our element dl to the point P. And theta? Well, that's just the angle between the direction of the current element dl and the position vector r. And the result? The magnetic field, dB, which is perpendicular to both of them, pointing into the page in this drawing.
So if we just talk about the magnitude or the strength of this little magnetic field, dB, it depends on four really simple things. 1. It's proportional to the current I. Makes sense, right? More current, more field. 2. It's proportional to the length of our little element, dl. 3. It depends on the angle, specifically on sine theta. And 4. Look at this. It follows the inverse square law, just like the electric field and gravity. It gets weaker as 1 upon r squared. Simple, hai na?
Theory is all well and good, but we really understand physics when we solve problems. So let's take a very simple example, one from your NCERT book itself, to see how we can actually put this law to work. Okay, let's look at this problem. It's taken straight from your textbook, so it's a good one to practice. We've got this tiny current element right at the origin, and it's carrying a current of 10 amps. Our job is to find the magnetic field it creates at point P, which, as you can see, is on the y-axis, half a meter away.
Now remember, solving any physics problem is just a step-by-step process. Don't panic, just follow the steps. Step 1. Let's list everything we know. The current I is 10 amps. Our little length element dl is 1 centimeter, which we'll have to convert to meters. The distance r is 0.5 meter. Now what about the angle theta? Well, the element is along the x-axis and the point is on the y-axis. So the angle between them is 90 degrees. And sine of 90 is 1. ठीक है? So for steps 2 and 3, we just plug these values into our magnitude formula. Step 4 is the calculation part. And for the final step, number 5, the direction. Our element dl is along the x-axis, so that's the I cap direction. Our position vector r is along the y-axis, the j cap direction. And from our vector classes, we know that I cap cross j cap gives us k cap, which means the direction is along the positive z-axis. Simple as that.
And there you go. After the calculation, we find that the magnitude of the magnetic field is 4 into 10 to the power minus 8 Tesla. Please remember the unit Tesla. It is very important. And the direction, just as we figured out, is along the positive z-axis. Bilkul straightforward. Okay, now I want you to pay very close attention to this next part. I call these the silent killers. These are the common mistakes and misconceptions that so many students make in exams, and they quietly steal your marks. So let me guide you so you don't fall into these traps.
Let's go through these one by one. First big mistake. Students think dB points in the same direction as r. Bilkul nahi, not at all. It is always perpendicular to the plane that contains both dl and r. Remember your right-hand screw rule for this. Second mistake, thinking the field is equally strong in all directions. That's wrong. It clearly depends on sine theta. So if your point is right on the axis of the wire, either in front or behind, the angle theta is 0 or 180 degrees, and the magnetic field there is 0. And the last trap, is current a vector? No. Current I is a scalar quantity. The direction is captured in the length element vector, dl. Please remember these 3 points very carefully.
All right, we've come a long way. We're almost at the end. So now let's put all the pieces together and see how this very important law connects with some of the other big ideas in physics that you've already learned.
You know, one of the best ways to understand a new concept is to compare it with something you already know well. And this comparison with Coulomb's law is just fantastic for that. Look at the similarities. Both are long-range forces and both follow the inverse square law. But now look at the differences. The source for an electric field is a scalar, just a charge q. But for a magnetic field, the source is a vector, our current element IdL. The electric field points along the line from the charge to the point, but the magnetic field is perpendicular to the plane. And finally, the magnetic field has this angle dependence, which the electric field from a point charge doesn't. This table is a brilliant summary for your revision.
So if we have to summarize our entire discussion, here are the 5 golden points you must take away. 1. Moving charges or currents are the source of all magnetic fields. 2. The Biot-Savart Law helps us calculate the field from one tiny piece of that current, IdL. 3. This field, dB, is always perpendicular to both dl and r. 4. Your best friend for finding the direction is the right-hand screw rule. And 5. The constant in the formula is mu naught upon 4 pi. If you just remember these 5 points, you are set. And to end, let me leave you with a final thought. We have just learned how one tiny insignificant element of current creates a tiny magnetic field. Now, just imagine, what if we add up the effects of not one but millions and millions of such elements, and we arrange them carefully, in circles, in loops, and in long coils? What kind of powerful, useful, magnificent magnetic fields could we create then? Well, that question, that leads us directly to our next topics, the magnetic fields of loops, solenoids, and the entire world of electromagnets. But that is a story for another day.